Well, so now we are ready to solve the exercises on Diophantine equations. So in this first one, we are given three equations and we have to say whether each one of them is solvable or not. And for that, let us also recall that solving a Diophantine equation, for example, this first one, means finding out integers x and y that will satisfy this equation. So let's see the solution. Let's start. Part A. Now from theory we know that this equation is solvable if and only if the greatest common divisor of these coefficients 6 and 51 divides 22. So that means we have to find the GCD. We have this equal to, we have to find the value, and in finding out this GCD value you can follow one of the two procedures. One of them of course is just blindly applying the Euclidean algorithm, in which you divide repeatedly. For example, you are going to first of all divide 51 by 6, you will get some remainder, then you divide 6 by that remainder, you will get another remainder, then you keep on doing this process until you get till you get the zero remainder. The last non-zero remainder from theory we know is the GCD value. But here for this particular case the integers are rather small and we can factorize them quite easily, and that will help us calculate the GCD more quickly. So from the prime factorizations we can just simply see that the GCD is 3, and 3 of course does not divide 22, since 3 does not divide 22, the equation 6x plus 51y equal to 22 cannot be solved. In the context of this exercise, this last sentence makes sense. If you just simply write the equation cannot be solved, then that is clearly false. The Diophantine equation cannot be solved. That is, we will never get integers x and y for which this equation is satisfied. For real numbers you can of course have, for example, if you take x equal to 0, then y equal to 22 divided by 51. These two values give you a solution, but that is not an integer solution. But anyway, this cannot be solved. So now we see part B. In part B, just like that, just like part A, we have to calculate the GCD of 33 and 14. Three times 11 and 2 times 7, no common prime. So in this case the GCD is 1, and that is why here the equation will have a solution, because 1 divides every integer, so 1 also divides 115. We have just been asked to ascertain whether the equation is solvable or not. Even if it is solvable, like in this case, we are not to find the solutions, since 1 divides 115, the equation, or it would be better if we write the Diophantine equation. Can be solved or is solvable. Next, part C. Here the numbers are 14 and 35. Here we do have 7 common, but 7 does not divide 93, which you can verify. Since 7 does not divide 93, the Diophantine equation, I'm writing in short because I already have the equation here. Luckily it has appeared here itself. Is not solvable. So that is just the solution. Now let's see the next one. Determine all solutions in the integers, of course. Of the following Diophantine equations. Here also 3 equations are given. The first one is 56x plus 72y equal to 40. Then part B, 24x plus 138y equal to 18. And there is one more. C. 221x, okay, plus 35y is equal to 11. Now here in this one we have been asked to actually find the solutions, all the solutions in fact, whenever the equation is solvable. So the procedure begins just like the previous one. We have to first of all see whether it is solvable or not. Anyhow we have to find the GCD, because from the GCD, in case it is solvable, from the GCD itself we will find any one particular solution. Then in terms of that one solution we are going to express all the other solutions. So let's see the solution. We have GCD of 56. Oh, here the numbers are, if you want you can in fact find the GCD by using the previous method, that is factorizing this integer. These are not extremely large, so large that they cannot be factorized somewhat quickly. They can be factorized, of course. These are very small. In fact, we can do it by hand. However, if you follow that method, then you will then have the difficulty of expressing the GCD as a linear combination of the given integers, which you in fact need in order to find any particular solution in case the equation has a solution. So that's why here it's better to use the Euclidean algorithm, that is you repeatedly divide until you get S0 remainder. So no, we cannot write like this. Instead we will have these equations. Let me just simply copy the equations, that way it will be somewhat quick. If you know me, you know that how bad I am with these actual numerical calculations. So that's why I am resorting to copying them. So in the next division we have a zero remainder. So that means what we have done, we have first of all divided 72 by 56. The quotient is 1, the remainder is 16. The remainder by definition has to be a non-zero integer which is less than the divisor 56, 16 is. And then we divide the previous divisor 56 by the remainder. So we get 3 times 16 plus 8. So here the quotient is 3 and remainder is 8. Then we divide the previous remainder by the current remainder, and doing that we get 0 remainder. So the last non-zero remainder 8 is the GCD. Hence by the Euclidean algorithm, what is happening? It's getting fainter and fainter. I think its life is almost over. I have to replace it with a new one. Hence by the Euclidean algorithm, see the difference? The GCD of (56) and 72 is 8. Which one can find by factorizing these integers also, but now we have to do the back calculation in order to express 8 as a linear combination of 56 and 72 with integer coefficients. And one more thing you should notice before doing all those things is that 8 divides 40, so actually the equation is solvable, since 8 divides 40, the given, if you do not feel like writing the actual equation, you can just simply write the given equation. The given Diophantine equation is solvable. Okay, now let us express 8 by going through this equation in the reverse order. Now 8, first of all, using this equation, of course you can never use. For our purposes now it is useless. So in place of 8 we can write 56 minus 3 times 16. 3 times 16. So that means we have used this equation, then the previous one, and in using the previous one we are going to replace the remainder that we have in the previous one with the equivalent expression, that is 56 minus 3 times, in place of 16 we are going to write 72 minus 56. And now you arrange things. So minus 3 times minus 1 is going to give you 3. That 3 plus 1 is 4. So 4 times 56 or 56 times 4, same thing, plus minus 3 times 72. Okay, so we have ended up expressing 8 as a linear combination of 56 and 72 with integer coefficients. Now in order to find a solution to this equation, what you have to do is, you can I think almost see, you have to multiply both sides by 5 so that we have 40 on one side, and on the other side we keep 56 and 72 like they are and absorb that 5 with these other integers, and that way we will get one solution. So doing that, what I said just now, so multiply on both sides by 5, so we will get 56. Let me switch the order. I write that 4 on this side. 4 times 5 actually, so 20 plus 72 times minus 15. So this gives us a solution. We can take x equal to 20 and y equal to minus 15. Hence x naught equal to 20 and y naught equal to minus 15 is a particular solution to the given Diophantine equation that need not be written, it's understood. But this is not the only solution. In fact, there are infinitely many solutions, and now we are going to express all of them in terms of this one. So any solution x comma y is given by, what was the expression, x equal to x naught plus b divided by d. Let me write it here. X equal to x naught plus b divided by d times t, and the y part is y equal to y naught minus a divided by d times t, where t is an integer. and D is the GCD. And our general equation is just this: ax plus by equal to C, where C is the right hand side. For us that is 40. D divides C. Okay, so now we are going to use these expressions. So our x naught is 20 plus, just for the sake of clarity, let's write what B is in this case. I lost the equation now. So the equation is simply, it was this: 56x plus 72y equal to 40. Yeah. So that means our A is 56 and B is 72. 72 divided by 8t, that means this is plus 90, and y is equal to y naught is minus 15 minus A divided by D, that is 56 by 8 times t, that is minus 15 minus 7t, and you have to also mention that here t is any integer. In fact, varying t, you are going to get all the solutions, and one of those solutions is this one, which you get for the choice t equal to 0, where t varies over the set of integers. So that is part A. Next, part B. In part B, the equation is what? 24x plus 138y equal to 18. Let me write it here somewhere. Let me write it here itself. It's not a part of the solution. I am simply writing it for us to be able to see. 24x plus 138y equal to 18. Okay. So in all these three equations, it turns out that they are solvable actually. So we have to find the solutions in each case. So just like before, we first go through the procedure of our Euclidean algorithm in order to find the GCD. We have, so the relevant set of equations in this case is this. So we are first of all going to divide 138 by 24. Doing that, we get this: 138 equals 5 times 24 plus 18. Next, we divide 24 by 18. So 24 equals 18 plus 6. Or you can show the quotient plus 6, and in the very next step we have 0 remainder. So that means our GCD is 6. So by the Euclidean algorithm, I am not again writing. So GCD of 24 and 138 is 6, and 6 divides 18, so this equation, like before, has a solution. Since 6 divides 18, the given Diophantine equation has a solution. Now that back calculation. 6 is equal to 24 minus 18. Now we replace 18, so this one we have used here. Now the next one, which is the only one left. So in place of 18 we are going to now write 138 minus 5 times 24. So we get 6 times 24 plus minus 1 times 138. So now in order to get 18 on one side, we have to divide on both sides by 3. Hence, doing that we get 18 equal to 24 times 3. So that means 18 again, plus 138 times minus 3. Thus x naught equal to 18. If we have the equation in front of us, then it's rather easy to recognize what is x naught, what is y naught, what is a and what is b. Otherwise we may really get confused with these values. So x naught is 18 and y naught equal to minus 3 is a solution. Is a solution a particular solution? Same thing. Is a solution to the given Diophantine equation. And now we write all the solutions. Hence, all the solutions x comma y are given by x equal to x naught, that means 18, plus b divided by d, that is 138 divided by d. Our d was 6. No? Yeah, I quickly forget everything. D is 6. So this is 18 plus 23 t, and y equal to y naught. Y naught is minus 3 minus a divided by d times t minus 4t, where t is an integer. So that is the general solution. Putting t equal to 0, we get this particular solution where the x component is 18 and y component is minus 3. Finally we have C, and in C the equation was this: 221x plus 35y equal to 11. 221. Okay, anyway we will see. We have, so first we divide 221 by 35. Doing that, what do we get? 6 times 35 plus 11. Next we divide 35 by 11. So the closest we can reach 35, we can be to 35 by following the multiples of 11 is 3 times 11, 33. So that means the remainder is 2. Then you divide 11 by 2. So here we are going to get 1 ultimately. I can see that. Five times 2 plus 1. Although the next one need not be written, but just for the sake of completeness I write quotient times divisor. Let's maintain that order also. Plus 0. So the last non-zero remainder is 1. So the GCD is 1. That means 221 and 35 are relatively prime to each other. So this is equal to 1. Since 1 of course divides everything, 1 divides 11, the given Diophantine equation is solvable or has solutions. Now, okay, so now it's time for expressing one as a linear combination of the given integer. So we use this one first. So 1 is 11 minus 5 times 2. Next we use this one and we replace 2 with 35 minus 3 times 11. And we are not stopping here itself, because we have to use another equation. Another equation is there. So before you do anything, you first do whatever needs to be done here itself, and then only you use the previous equation. By that what I mean is that, you see, you collect the 11s together. Here you have 1 11, and this term will give you minus 5 times minus 3 is 15, 15 11s. So 16 times 11 minus 5 times 35. And now you replace this 11 using this equation. If you want, you can use this equation here itself in 2 places, here as well as here, but that will only make matters worse. So now 16 times, now in place of 11 we are going to write 221 minus 6 times 35. and we already have minus 5 times 35. That means we are getting 16 times 221, and what will it be? Minus 1, it turns out to be 101. 101 times 35. This type of calculations, which many of you can do with ease, I find difficulty. So it's a problem that I have. Okay, now this is not quite the equation that we want. We want 11, so we multiply on both sides by 11. That is going to increase the integers even more, I mean their values. Hence 11 is equal to 176, 11 times 16 times 221 minus, what will this be? 1111 times 35, and this gives us one particular solution. So a particular solution to our Diophantine equation is x naught is the one that is there with 221, that means 176, and y naught is the coefficient of 35 minus 1111. Do not forget the minus sign, okay, because the original equation has a plus here. So our A is 221 and B is 35. That also we should not forget. If we switch the order, then it will be a mistake. A is 221 and B is 35. So the general solution, instead of writing hence all the solutions to our Diophantine equation are this and this, you can also write, so the general solution to the given Diophantine equation is x equal to x naught, that is 176 plus b divided by d, and our b is 35. In this case d is just 1, so it will stay like that, and y is equal to y naught, that is minus 1111 minus a divided by d times t, where this, so that's just the end of our solution, and I end things here itself. We are going to solve more exercises in the next number theory update. Now before I end the video itself, let me also say something about the need for writing these things. I mean, if you are say preparing for some sort of examination, some test, something, some competitive exam or something where you need to actually write some solutions like this, it's better to write these things again and again. I'm not asking you to solve the same problem again and again, but at least you should practice these languages or how to write these things if you are preparing for an exam. Otherwise also there are benefits of writing like this. There are many benefits. The only thing is that you should keep in mind, you should not overdo it, so that you are just you put this in your mind that you have to write everything formally. You should strike a balance between being formal and being intuitive. So if you can strike that right balance, then life will be okay. But from an examination point of view, you should write these things, no matter how boring they are, because among the many benefits that this practice has, one benefit that is, I think, it is what you should do these things for, and that benefit is that when you write these things mathematically in words or as equations, you continuously train your brain mathematically. Okay, that you may not realize, but it's happening. When you are going on writing something down, if you just simply see, that's why we say we do not read mathematics. We read, of course we read, that's something in a proof, say a proof is given, we read what is written there, but then simultaneously we also write some equations. So when you are writing things down, it will not be passive reading, it is active reading. Okay, so that's just it. That's something, a little thing I wanted to say. So the next update is this coming Friday. So we have already gone through the cycle, not entirely. One more thing is there, that is graph theory. So again, let's go back to graph theory on Friday. So with that, I wrap things up for tonight. So see you next Friday. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.